Hi, my name is Tenavi. My collaborators are Gong and Kang. This talk is about some recent research trying to improve the reliability in using neural networks for optimal feedback control. So we want to design controllers for high-dimensional nonlinear systems. In this talk, we'll use an example from PDEs. Previous work has done things with aerospace, and there's many domains where you want to try to do something like this. One of the techniques that's been getting a lot of attention lately is supervised learning, in particular with using neural networks. And while this has demonstrated a lot of promise, if we want to really use this in real life applications, we need to make sure that this thing is reliable and safe and performs as expected. So in this talk, we'll try to answer or start to answer two questions. The first is, how does approximation accuracy in terms of trying to approximate the optimal control as a function relate to good control performance? And the second is, how can I try to design reliable neural network controllers so that I'm more confident and I trust my output better? So the problem that we're looking at is an optimal feedback control problem. We want to minimize this cost function over infinite horizon, subject to some nonlinear dynamics x dot equals f of x and u. And this talk will focus on a quadratic cost, but you can definitely generalize to other cost functions. So the way to do this, at least mathematically, is you want to solve a Hamilton-Jacobi-Bellman partial differential equation. This is a nonlinear PDE in n spatial dimensions, whose solution is the value function v. And that tells you the optimal cost to go starting at any point x. So if you can do that, then you get your optimal control, optimal feedback control, u star, as a function of the gradient of that value function. So this is a really nice theoretical framework for doing this. Unfortunately, in practice, it's really difficult because anytime you want to do this with a high dimensional system, you need, if you try to use a traditional discretization method, your discretized system, that size just explodes, right? So you can't do it. So what can we try to do? Well, if you're an engineer, our intuition is to linearize the system. You get x dot equals ax plus bu, and you can solve your Riccati equation, and you can get the LQR value function in control. So this is a quadratic value function approximation and a linear control law that has a lot of successful engineering applications, but it is suboptimal. And in the worst case, sometimes it's only locally stable. So if we intend to fly these things in highly nonlinear regimes, then we need to do better. And for that reason, there's been a lot of work trying to develop methods and algorithms to solve that full nonlinear HJB equation. And here I give a partial list. I'm not going to go into detail on these, but there are some references in that paper listed there. So the method I will go into detail on is supervised learning. And what this is trying to do is, okay, we can't solve this HJB equation directly, but what we can do is take a detour through Pontryagin's principle. So this is a 2-point boundary value problem. In this case, it'll be infinite horizon, that we solve forward for the state x and backwards for the co-state lambda. And you can do this independently for any initial condition, giving you the chance to mitigate the curse of dimensionality. And there's actually a lot of numerical solvers that lets you do this. So under some conditions, along that trajectory, that optimal trajectory x, you have a correspondence between your open loop optimal control and your closed loop feedback optimal control. You also can compute the value function, and you also know that the gradient of the value function is going to be equal to that co-state. So by doing this at many points, you can start to build a data set, which you can eventually use for supervised learning, where we will try to train a neural network approximation, VNN, of our value function. You could actually use different model structures in here. It doesn't have to be a neural network, but we'll call it a neural network for simplicity and consistency. So there's been a lot of work demonstrating some of the initial successes of this. And here's a list, which I think is fairly complete, but sorry if I missed you. So let's go into a little more detail. For generating data, we're going to sample some initial condition x naught, solve that 2-point boundary value problem up to a large final time capital T. And because this is an infinite horizon problem, we want to make sure that our finite horizon solution does a good approximation of that. So we'll make sure that the dynamics have converged to equilibrium and the running cost is sufficiently small so that integral isn't growing, right? If those conditions aren't met, then we need to increase our final time and resolve. If we are happy with our solution, then we can add it to our data set, which looks like inputs, xi, samples of the state, and along each trajectory, and then outputs, which are the value function, the co-state or gradient, and the optimal control at that point. And you notice that time has disappeared here because we're actually solving this infinite horizon problem. So the nice thing about Pontryagin's principle, really, and the reason that we think it's a good approach, is that you can solve each of these boundary value problems independently. You don't need to know the solution in nearby spaces to be able to solve this boundary value problem. And there's also a lot of numerical techniques for solving this open loop optimal control problem when the closed loop HJB, it's just really hard, right? So we think that this is a good way to go. And we like to call this causality free, because you don't need to know the solution at nearby points. And that causality free property lets you be free of a mesh. You don't need to build a new spatial grid. You can solve these BVPs in parallel. You can also make an independent data set to empirically validate your solutions. And we'll use that concept later. You can also do adaptive data generation, particularly making training data in a region that you really care about. And I'll refer you to a recent survey that we put out in Physica D this year that talks about a lot of different data generation methods for optimal feedback control. So we have data. Let's build a neural network. So here we'll use a standard feed-forward structure. There are many other architectures you might try, but we find this simple basic architecture to work well enough. And we'll try to model the value function using that neural network with that fancy curly N there. And it's parameterized by, we'll list as theta, and those theta represent the weights and the biases of your neural network. And one of the nice things about a neural network is you have automatic differentiation that gets you your gradient of the value function, and you can plug that in to your optimal control in place of the actual gradient, which you don't know. And from there, you are able to get your optimal or neural network feedback control, which approximates your optimal one. So previous work has shown that these neural networks have good approximation properties, even with a large state dimension. And they are able to be used online with really quick evaluation. So that gives us the chance that we could actually use this in a real-time application. Next, let's talk about how we train them. We have a set of training data that we talked about before by solving those boundary value problems. And we're going to minimize this loss function, which is 3 parts. We have the first term is just a loss V. This is a standard regression, mean squared error, where we try to match those value function data at every point. The next is a physics-informed regularization, where we try to learn the co-state or the gradient. And remember, that data comes for free every time we solve the boundary value problem. And this is nice because instead of just learning to fit points, we actually learn the shape of the value function at those points. So by incorporating that problem structure, we're getting a lot of extra information out of our data set and regularizing it in a way that's cognizant of the underlying structure that we want this value function to have. The last term there is something that tries to learn the optimal control added to those points. And this works directly towards our ultimate goal of getting a good feedback controller. Once you've done your training, we can take a test data set, which is independently generated. The neural network has not seen this before. You can plug it into your various error metrics, and you can get an empirical estimate of how good your neural network does in approximating these various things. And this is one of the nice things about the causality-free method, the causality-free approach, is this access to these different data sets. So knowing that my neural network does well when it sees unseen data gives me some hope or some confidence that it'll do well in a real situation, because you can't train for every possible situation. All right, so let's see this method for an application problem. So here we'll use control of a unstable Burgers type PDE. And we have 2 control inputs. They're active on these blue regions shown there in the spatial domain. And then we took some inspiration from a paper by Dante Calis, where we put in a unstable reaction term. because normally if you have a Burgers PDE, it just diffuses out into nothing and you'll be stable anyways. But adding this additional term there will make the origin unstable, makes the problem a little bit harder to solve, right? So this is a PDE. We'd like to transform this into a system of ODEs, and we do that by Chebyshev collocation. Here we'll use 64 nodes because you need a lot in order to resolve the dynamics. But also you can see now we have a 64-dimensional optimal control problem. Now that's quite large, but we'll see that these methods are actually able to handle it. Okay, so what we've done here is we've built some data sets of different sizes, and you can see the number of trajectories in each of those training data sets on the x-axis of these plots. So they go from 8 trajectories to 128. And each of those trajectories contains a few hundred data points in it. And since we're picking the initial conditions for these randomly, we want to generate many data sets so that we sort of account for the randomness in that generation and see what it does to our neural network accuracy. So we generated 10 data sets of each size. And for each of those data sets, we trained a neural network with a different random parameter initialization. So because neural network training is a really highly non-convex optimization problem, the results will actually depend on that random parameter initialization. So that's another area of randomness that we need to account for with this sort of statistical analysis. And we can see that the top graph is when we compare our control accuracy on a set of 400 test trajectories that the neural network hasn't seen, it does quite a bit better than LQR, especially as you increase the number of training data. This is what we hope for, right? Because we're now learning the full nonlinear optimal control instead of just in the linear one. And the training time of these, I want to comment, is also quite short. It's about 5 minutes for the longest of these networks. And that's really helpful if you're doing some kind of iterative control design process where you'd have to be training many, many networks in order to find a satisfying solution. So here's what it looks like in the closed loop system. So on top, you can see that Burgers PDE being stabilized to the origin. The second line plot there is the norm in the L2 space of that PDE value. And in the bottom two, actually, you can see the control, the neural network control is tracking the optimal quite closely. And for this problem, LQR does stabilize the system, but you can see if you look closely that it's doing like twice as much effort as the optimal or the neural network control. So while LQR does work, there is some benefit to be gained in terms of efficiency by using this nonlinear controller. So this is great, but what if we take that same initial condition and a different neural network trained on the same number of data points and has actually very close in terms of this mean test error, excuse me. And you can see this does really good up to about 50 seconds when something goes wrong and the state starts to take off from the origin. And then you end up at this other weird equilibrium that you don't like. So this is really not what we want, right? We want not just our controller to be performing well, but we need it to be stable. And we're like, okay, well, maybe this is just some freak occurrence, right? How often does this happen? Well, we can try to test that, and we'll take, what we do is we'll sample 100 initial conditions with some particular fixed radius. And then we're gonna, for each of those 50 trained neural networks that we had before, we're gonna simulate the closed loop system for each of those initial conditions. And what we plotted here is each circle is going to be a single neural network, and we plot the maximum of the norm of where all these closed loop trajectories end up. So if you're on the x-axis, all of those trajectories ended up really close to the origin. If you're off the x-axis, that's not good. That means you had some runaway trajectories like you see on the left side. And that x-axis, what we're plotting there is the mean control error. So further to the left means more accurate, further to the right means less accurate. So you can see there is a little bit of a downward trend towards the left. So as we expect, stability does improve with approximation accuracy, but it's not guaranteed, right? You have some neural networks right on the left that even though they're doing quite a good job overall, there may be one or more trajectories that did this runaway thing. And that's really not comforting, right? You don't want to be flying along in your airplane and suddenly it goes upside down. So we cannot have this if we're trying to design controllers like that. So to try to start to understand this, we'll look at a little bit of closed loop stability with these neural network controllers. And there's a lot of ways to think about stability. You can think about local stability near that origin, like a linear sort of stability analysis. You could use more semi-global stability analysis with Lyapunov functions. This is maybe important because we're trying to design controllers for highly nonlinear systems, right? And there's many ways the stability could come about. What conditions does it have to be stable? Do we know with certainty that it's going to be stable, or is it going to be probabilistic? And how do we get there? So we found a little bit of prior work on this. There's a group by this is Dario Izzo, I believe, and they've done some work on doing linear time delay stability analysis and some stability around a nominal trajectory. And then what we'll talk about today, two things. First is try to do a linear stability analysis by applying automatic differentiation to get a representation of our closed loop linearized system, and you can do standard linear tools on that. And then we also started to develop a little bit of a theory that connects the test accuracy of our network with the probability of stability. That's what we'll look at right now. First, we need a little lemma. Let's say we sample a bunch of points indexed by I uniformly from some domain D. And we'll take the maximum error of those. We'll call this our maximum test error and call it delta N. And what we're trying to approximate is the true unknown error delta, which we can think of as the maximum over the neural network control, the optimal control as continuous functions. And what you can see is because of this uniform sampling and some continuity, the maximum test error converges in probability to the true unknown error. A little bit more specifically, if I have some difference, epsilon, and I want to ask, well, what's the probability that my true error is going to be greater than my test error by this epsilon? And it's given by this function f of epsilon to the nth power, where n is the number of test points you used. And that f of epsilon is just the probability that one of my samples, any individual sample, lands far away from the true maximum. You take this to the nth power, that's your probability that you're going to be not seeing your true maximum, right? And what we do with this is the following result. So let's suppose that our test maximum error is less than delta plus, where this delta plus is kind of like a worst allowable deviation from our optimal system. Specifically, what that means is like any deviation from your optimal control worse than delta plus is going to make the thing unstable. And this delta plus is something actually you can compute ahead of time if you know things about Lipschitz constants and stuff like that. So if you have that condition satisfied, then the closed loop system, the whole closed loop system, all the trajectories starting close enough to the origin are going to be ultimately bounded with some probability that you can compute based on the difference of your worst allowable deviation and your test error. So it's this f that we got in the previous lemma of that buffer between those two. And that's going to be taken to the nth power. And to remind you what ultimate boundedness means, that means if I start in that green circle, I'm going to converge exponentially to the yellow circle. And then once I get there, I'm going to stay inside. There's no guarantee I'll get to the origin or anything like that. Maybe I'll go to some other equilibrium, or I'll go to some orbit, or bounce around chaotically. But what this says is that if I have a certain test error, there's some probability that my controller is going to make the overall system stable. So this is like a system-wide property. And we think that this qualitatively explains something what we've seen before, whereas we had those two controllers that had similar test error, but one of them tended to be stable and one of them was unstable. This isn't the whole picture, but we think this is a little bit of a start. Let's shift gears a little bit. We talked a little bit how to think about stability, but now how can we make the whole controller we design more stable? So before we used neural networks, and we found that this really improved this gave us good performance. And what we'll do now is add on an LQR term that gives us reliability. So all this is we take a LQR and we apply this function to it with a trainable parameter C. A small parameter means that we're going to add essentially the plain quadratic term that comes from LQR. And a large C means that the LQR part will get weaker as we go further away from the origin. And this is nice because for highly nonlinear systems, the LQR component, we don't want to rely on it too much far away from the origin because it's not going to be a good approximation. And that C is something we tune during optimization, and it gets learned along with the rest of the neural network. So we think that this will keep the performance of the original neural network, but also add in some reliability by giving it the scaffolding of LQR to learn from. And we'll look at that, what that reliability means in just a second. Okay, so if we keep this, we have this experiment that we did earlier with training many different neural networks. We'll also train a QRnet for all those same data sets. And you can see that by evaluating them against the test data set, you slightly improve the performance relative to the neural network, with more performance improvements gained when the training data set size is smaller. That seems to be because this QRnet has a scaffolding of LQR to learn from. It's not learning from scratch. The training time is also comparable, and this is good. If we start by looking at the linear stability of the system, we're going to find an equilibrium point for each of these that's close to the origin. There might be many equilibrium for each of these, and they're not going to be necessarily at the origin, but we can do some root finding, find one that is close to the origin, and look at the local stability there. Hopefully this thing would be, if you plot the largest eigenvalue, hopefully it's going to be negative, right? But unfortunately, if you look at the plain neural networks, those blue bars, you see that unless you train with a lot of trajectories, there's a pretty good chance that actually you're going to be unstable. You're going to have a positive eigenvalue. On the other hand, for QRnet, you don't see that. You see that overall, even if you train with very, very few data, because of the LQRs helping you out, you're going to have locally a pretty stable controller. And this is a really nice property because it looks like you are improving local stability and approximation accuracy when you're training with small data sets without sacrificing anything. Now, if we look at the more global stability kind of analysis, if we again take those 100 initial conditions and we simulate the system for those initial conditions, and we plot now the maximum of where those trajectories ended up, we'll see that basically all the QRnets ended up on the x-axis where it's stable. So that upper blue cloud, there's only just 2 QRnets and they had really bad approximation accuracy. Whereas basically every QRnet ended up in the stable group. So we can see this kind of like QRnet is roughly decoupling stability from accuracy. So when you're training, even if you end up with something that's not very accurate in terms of approximation accuracy, you could still have a stable controller. And this is really nice. If you have a sharp eye, you'll notice that the LQR is actually doing a great job stabilizing the system. So why do we bother? Well, for this problem, at least, we'll see that the neural network and the QRnet, if you look at just the stable ones, they're going to do a lot better than LQR. So if you compare the percentage of suboptimality relative to the optimal control for each of the stable networks, and we'll look at the averages on top and the standard deviation as on bottom, everything in those orange boxes is doing better than LQR. So overall, it seems to be that you can gain a lot of performance by bothering to train a nonlinear optimal controller. And QRnet is nice because it makes sure that this controller you train is going to be stable. You're not wasting your time. All right, so to summarize, we think that this neural network-based feedback is a promising approach, but it definitely requires us to take a closer look at stability because these neural networks are really hard to understand. We've tried to design or develop a new perspective that connects the test accuracy of a neural network to a kind of probabilistic stability. This is interesting because it's probabilistic stability that appears in a deterministic system. We also introduced this QRnet architecture that improves the robustness during training towards small data sets and also the closed loop stability of the final controller. In future work, we'd like to look at different analysis, for example, the stability of individual trajectories versus a system perspective, and then also try to design better neural network architectures that have some built-in stability guarantees. Thank you very much for listening.